Right, in Chapter 14, Section 5, we're going to look at chain rule for multivariable functions. So in the first one we have w, and it's a function of four variables, x, y, z, and t, but then x, y, z, and t are functions of subvariables called u and v. So we can build what's called a tree. So it says w branches off to x, y, z, and t, and then each of those variables branch off to u, v, and uv, and uv, and uv. So first off, this problem is really simple. They just ask you, okay, how many variables are there? So there turns out to be four variables. So the variables we're interested in are these four. And so you just have to type 4 in the blank. And then m is 2 because that's the number of subvariables for each of the main variables. Okay, so let me explain how these work. So let's say we want to calculate the partial derivative of w with respect to u. Well, we have to go down each branch to get to u. And every branch we go down is going to have a partial derivative on it. So the first branch from w to x would be the partial derivative of w with respect to x. Then from x to u would be the partial derivative of x with respect to u, and you multiply those two together. So that's going to be this branch right here, dw dx times dx du. Maybe I should use color here. Then in green, we're going to have dw dy, because I went from w to y, and then we have dy du, because I'm going from y to u. So dw dy, dy du. Then we go down the z branch, so let's make it purple. So I have to first go down dw dz. Then I go from z to u, so it would be dz du. And that's these two right here. Then the last one, we're going from w to t and t to u, so it's dw dt and then dt du. And again, these are all being multiplied, dw dt, dt du. And that's just the branches going to u. If I want to go to the branches for v, then I have to do this one. And it's very, very similar. The only thing that will change is the second term in each of these. So it's still going to be dw dx, dw dy, dw dz, dw dt, but then the second term's changed to v's on the bottom. Okay, so that's the idea. So we're going to use these trees and the knowledge we gained from the last section of how to take a partial derivative to calculate some of these things. Okay, so for problem 2, it says u is x5 y plus y squared z9, and then x is a subvariable r s squared e to the minus t, y is subvariables r, s, and t, so we have y is r s squared. I think I screwed this one up. X was just r s e t. R s e t. Y is r s squared e minus t. And then z is r squared s times sine t. And they want us to find du ds. And they gave us the tree. It's partial u, partial x, partial s. So there's 6 things we have to find. So let's find, and actually let's only find the ones they want us to. So they want us to find du dx, and that will go in this blank right here. Then they provide for us dx. Here, let me do this more intelligently. Let me box what they box and parentheses what they parentheses. So that's the box, this is the parentheses right here. Then they gave us the next two completely. Then they gave us this one, and they want us to find it. So we only have to find two things. we have to find du dx, which is pretty easy. If I look at the u equation and I have x be the variable and all other letters be constants, I'm going to get 5x4y, and then y squared z9 will just go away. So that's what I get for that box right there. Then they want dz ds. dz ds is the partial derivative of the z equation with respect to s, which would just be r squared times the sine of t. So if s is the variable, the derivative of 1s is just 1, and so we're just left with r squared times sine t, which we put right there. Okay, then they want us to actually calculate these things. So they say, what happened? They say let r equal 2, s equal 1, and t equal 0. Well, if you plug those three things into these equations for x, y, and z, you will get x is 2, y is 2, and z is 0. So if you plug these 6 numbers into these letters above in this long equation, you will get, so 5x4y, you just have to plug in 5, x is 2 to the 4th, and y is also 2, and you will get 160. Then they tell you RET becomes 2, x5 plus 2yz, that's done for you, that's done for you. So you just have to calculate r squared, oh no, everything's done for you. So you just have to add these numbers together and get that right there. So there's actually a lot to this problem, but they broke it down and only asked us to do a few parts of it. So it actually becomes manageable. I mean, it's not that bad, but we could have done the whole thing. And we will do some where we do the whole thing. Okay, for problem 3, it says z is equal to x squared plus y squared plus xy. Then they tell us x is sine t and y is 9et. And they want us to find partial z, partial t. Well, that's going to be derivative of z with respect to x times derivative of x with respect to t. It's going to be the derivative of z with respect to y times the derivative of y with respect to t. So there's a pattern here. First is we need x and y. So it's always going to be dz dx and then dz dy. Then the next term will always have, if I wrote dx on the bottom, I need dx on top, because I need these dx's to cancel, so I have dz dt and dz dt. So notice dz dy, then the dy's on top, so they would cancel, bottom and top, and I get dz dt. So these are 4 things. So let's do this. Partial derivative with respect to t. dz dx, I look at the z equation, x is the variable, so it becomes 2x, y's go away if y's are constants, so y squared becomes 0, then the derivative of xy would be just y. Now I do dx dt, the derivative of x with respect to t would be cosine t. So the derivative of sine is cosine. So that's the first 2 terms. Then plus dz dy. Now x squared would go away and y squared would become 2y, and plus xy, the derivative of that would be x, times dy dt. The derivative of 9et is 9et, so it doesn't change. And I guess that's it. So I just took all that and typed it in, and that is the derivative of z with respect to t. Okay, problem 3. Problem 4 is going to be extremely similar. We have a w equation, x e to the y over z. Then they tell us x is t to the 3rd, y is 8 minus t, and z, wish I had room there, z is 5 plus 9t. And what we're looking for is dw dt. Well, that's partial w with respect to, we got three letters here, so with respect to x times dx dt plus dw dy dy dt plus dw dz times dz dt. Okay, the partial derivative of w with respect to x, the x would just go away and you're left with e to the y over z times dx dt. dx dt would be 3t squared. Okay, now partial derivative of w with respect to y. Maybe I should write this a different way. This is going to be x e to the y times z to the minus 1. Let's write it like that. Okay, so the partial derivative of w with respect to y, x and z are variables, or constants. So this is just going to be x, but this, I'll leave it, actually we'll leave it as 1 over z. This 1 over z is a constant in front of y, so that's going to come down. So this is really x times 1 over z times e to the original thing unaltered, y over z. Okay, that's dw dy. Now dy dt would be just minus 1. So the derivative of y with respect to t, the 8 goes away, and minus t becomes minus 1. Okay, now dw dz, that's where I need this one here. The derivative of this would be x is a variable. We need to have, where are my notes on this? The y is a constant, so it's going to come down. But then we're going to get e to the y over z. But then we have to take the derivative of this z minus 1. So then it's times the derivative of z minus 1 would be minus z to the minus 2. That's the hardest one in here. Then it's times the derivative of z with respect to t, which is just 9. Okay, so let's see what we can simplify. This would be 3t squared e to the y over z. It's not very easy to type this answer in either. Then we have minus x times 1 over z is x over z times e to the y over z. Now this one, we have 9xy with a, let's see, this is a minus, so it's going to be minus 9xy on top divided by z squared. So that z to the minus 2 will come down, and we're going to get e to the y over z. So notice each term has an e y over z in it, and then they have various different coefficients. Let's see if we got everything correct. 3t squared minus x over z minus 9xy over z squared, and they all have an e y over z there. Let me make sure you're fully on board with this. Let me do this one in green, because this one's the hardest one to see. The derivative of w with respect to z. First we do the derivative outside. The derivative of the outside is x is a constant, y is a constant, it comes down in front, and then we leave this exactly the same, e to the y over z, but then we have to multiply by the derivative of this right here. And that's going to be, the minus 1 will come down, you subtract 1 from the power, minus 2, and so that's where we got that. And so we have the x and the y, we have the negative z to the negative 2. And then you have to use some algebra to clean it up. Okay, that's problem 4. if I remember right, this one's not as bad. Oh, maybe it is actually. Z is equal to the arc sine of x minus y. Well, well, I'll write it when we get to it. X is s squared plus t squared, and y is 3 minus 8st. And they want dz ds. dz ds would be dz dx dx ds plus dz dy dy ds. This is going to equal dz dx. So if you have the derivative with respect to x of arc sine of x, that's equal to 1 over the square root of 1 minus x squared. So the derivative of arc sine of x minus y is 1 over the square root of 1 minus that entire bubble, x minus y squared, times the derivative of the inside bubble with respect to x would be 1. So this is times 1. So again, chain rule. So what we have to do is write the derivative of this outside, which would be all of this, times the derivative of the inside, which would be right here. And let's actually write it as 1 minus 0. All of that is dz dx times dx ds. That one's easy. Dx ds would just be 2s. Okay, then it's plus dz dy. Now we can use symmetry here. This is going to be very similar. It's going to be 1 over the square root of 1 minus the quantity x minus y squared. But now it's times the derivative of the inside where y is the variable, so it's going to be 0 minus 1. Then it's times dy ds. dy ds would be 3 goes away, s goes away, it'll be negative 8t. And if you look, this 1 and this 2s will go on top, so I have 2s over that same denominator that we have, and then this negative 1 and negative 8 will cancel, and so I get positive 8t on top of the exact same denominator. Okay, now we're going to find dz dt. Well, that's going to be dz dx dx dt plus dz dy dy dt. Okay, and it's going to be really similar. So we're going to get dz dx is going to be, well, it's the exact same thing. It's going to be 1 over the square root of 1 minus x minus y squared. And then dx dt is going to be 2t plus dz dy is the exact same thing. It's going to be minus 1 because of this minus 1 here over square root of 1 minus x minus y squared times dy dt. dy dt 3 goes away, 8s is now a constant, t goes away, so it's minus 8s. And just like before, this 2t will go up here, so we get 2t over that. This minus 8s will combine with this minus 1. The minuses will cancel. Positive 8s over the same denominator. Okay, that's problem 5. Okay, problem 6 is just going to use numbers, so that's kind of nice. We don't have to do a bunch of algebra with letters because we're just going to have numbers. So it says Ws of t is f of u of s of t v of s of t, where f, u, and v are differentiable, and the following applies. Okay, so they want us to calculate, let's see here, ws. How did I write this out? I want to write this out so you can see it better. 6. Okay, so what they really want is they ws, I'm going to write this right here. Ws is really the partial derivative of w with respect to s. But that's going to equal the derivative of w with respect to u times du ds. Plus, our other variable is v. So it's dw dv dv ds. But in this sort of nomenclature where you type the derivative as a lowercase letter subscript, dw du is really w they're using f, so dw du is really fu, du ds is really us, and then dw dv is fv, and dv ds is really vs. And we have numbers for all of these things. So it says fu is 3, us is 1, it says fv is 4, and vs is 2. So we're just going to get 3 plus 8, which is 11. Okay, now they're going to want us to find wt. Wt is going to be, let me just jump to this nomenclature, it's going to be fu ut plus fv vt. And fu was 3, ut is now 0, according to this right here. Fv we saw before was 4, and vt is -1. So this is going to be 0 minus 4, which is minus 4. Now, the only reason I can do this is because these are all being evaluated at the same point, -5, 5. And in fact, u and v at -5, 5 are -4 and -3, which are then plugged into the f function to give us the 3 and the 4 there. So I could play a little fast and loose with that because all of these partial derivatives were evaluated at the same point. So that's 6. Doesn't have to be too hard of a problem if you kind of see the pattern there, and then you can kind of plug and chug. Okay, 7 says use this equation to find dy dx. Well, what's this equation? So if you click on that, I'm not going to because it's going to draw us away from the screen. It will say this, dy dx is equal to the negative of the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. But in the nomenclature that I think is a little easier to write, this is minus f little x over f little y. So it's partial x and partial y. So we have an equation. Now to make this into a function, we're going to write this as 2y cosine of x minus x squared minus y squared. So we're going to pull these two over here and write it as one function. Now we can do the derivative of this with respect to x. So again, y's are constants, x are variables. The derivative of cosine is negative sign, so we pick up a minus sign. 2y is a constant, sticks around. Derivative of cosine is minus sign. Then we get minus 2x, and the minus y squared goes away. Then we get fy. And that's going to equal, now cosine x is a variable that just hangs around for the ride. Y is going to go away, so it's going to be 2 cosine x, and this one's going to be minus 2y. And we're going to put this in a ratio, and we're going to put a negative in front of it. So we're going to have this equals minus, from this minus, fx, which is minus 2y sine x minus 2x, all over fy, which is 2 cosine x minus 2y. Now I'm going to apply this negative to these two negatives, and which will make it positive. So we'll get negative fx over fy is 2y sine x plus 2x divided by 2 cosine x minus 2y. Then the last thing I did was I said, oh, there's a 2 in every single term, so you can literally just go in and cross off all the 2's, and the final answer is y sine x plus x over cosine x minus y, right there. Okay, so that one's not too bad. You're just using partial derivatives that we have been getting better at. Okay, problem 8. We've got a temperature at a point xy is capital T xy measured in degrees Celsius. A bug crawls so that its position after t seconds is given by x equals square root of 1 plus t, y equals 8 plus 1/8 t, where x and y are measured in centimeters. The temperature function satisfies partial derivative of temperature with respect to x at 0.39 equals 9, and partial derivative of temperature with respect to y at 39 equals 7. How fast is the temperature rising on the bug's path after 8 seconds? What they want is the partial derivative of temperature with respect to time. That's going to have the partial derivative of temperature with respect to x times the partial derivative of x with respect to time, plus the partial derivative of temperature with respect to y times the partial derivative of y with respect to time. Okay, but we have to find dx dt and dy dt. Dx dt would be equal to, let me write x as 1 plus t to the 1/2 power. So this is going to be 1/2 1 plus t to the minus 1/2 power times the derivative of the inside, which is just 1. And I'm not going to simplify that because we're going to plug in numbers very shortly. Then we find dy dt, and that one's a little simpler. The function's 8 plus 1/8 t. 8 goes to 0, 1/8 t becomes 1/8. Okay, now they are saying that time is 8 seconds. So that's how they got this 0.39. They plugged in 8 into these functions, so they got x is the square root of 1 plus 8, which is the square root of 9, which is 3. Then they plugged in 8 into this function for y, 1/8 times 8, which is 8 plus 1, which is 9. So that's how they got this tx is 39. Well, we can plug the time of 8 into dx dt. So what we have is dt, d capital T with respect to little t, is this dt dx is, this whole thing right there is capital Tx. But they told us that that was 9. So we're going to write 9 times dx dt. Well, that is 1/2 1 plus t, which is 8, raised to the minus 1/2. Times 1 doesn't change it, so we'll leave it like that. Plus, this dt dy is really capital Ty, which they told us was 7. So that whole term will become 7 times dy dt. It's not dependent on time, it's just 1/8 constantly, so we get 1/8. Now this turns out to be This is 1 plus 8, which is 9. So you're going to get, let me actually write this out. You're going to get 9 on top divided by 2 times the square root of 9. And then this one is 7 over 8. Well, this one just becomes 9 over 6. Square root of 9 is 3 times 2 is 6 plus 7 over 8. And in decimal form, that turns out to be 2.375, which they want you to round to 2 decimals. We'll call it 2.38. So basically, the temperature is increasing by 2.38 centimeters Celsius per second as this bug is crawling around this, what is it even crawling around, some bowl or something? So yeah, this bug is moving on this path and the temperature is increasing on the path by around 2 Celsius per second. Okay, that's problem 8. Problem 9, the radius of a right circular cone is increasing at a rate of 1.4 inches per second, while its height is decreasing at a rate of 2.7 inches per second. At what rate is the volume of the cone changing when the radius is 120 and the height is 190? So the first thing you do is you look up the volume of a right circular cone. And just like I did, I Googled it because I don't have that memorized. But the volume of a right circular cone, according to Google, is, and I have it written down, where is it? Here we go. Pi r squared h of the cone over 3. Okay? So we want the change in this volume with respect to time. So it's going to be very similar to the last problem. We're going to do the change in the volume with respect to the radius times the change in the radius with respect to time plus the change in the volume with respect to its height times the change in the height with respect to time. So first we find the change in volume with respect to radius. It's going to be 2 pi r h over 3. Then we find the change in volume with respect to height, which is going to be pi r squared over 3. So the h just goes away, and we're left with pi r squared over 3. And it says r is 120 and h is 190. So we're going to get the change in volume with respect to time is, it's dVdr, but dVdr is 2 pi r h over 3, so it's going to be 2 pi times the radius, which is 120, times the height, which is 190, divided by 3. Okay, all of that is dVdr, right there. Now dr dt is the change in radius with respect to time. Now that's a number that they gave us. It says the radius is increasing at a rate of 1.4, so this is 1.4. Okay, then we have plus dVdh. dVdh is pi r squared over 3, so it's pi radius squared 120 squared all over 3 times the change in height with respect to time. Now be careful, decreasing. That means it's a negative. So we have negative 2.7. Okay, now this problem just becomes a lot of arithmetic. And the issue is they want you to keep these pi's along for the ride. So you want to basically calculate all these numbers and not calculate pi. So don't type 3.14, don't type your pi in your calculator. Just take 2 times 120 times 190 times 1.4 divided by 3 with a pi on it. Then over here take 120 squared times negative 2.7 divided by 3. And then you'll have two numbers with pi that you can then combine, and you should get something like that, 8320 pi inches cubed per second. And it's helpful to look at units again. This has a unit of inches. This has a unit of inches. This has a unit of inches per second. So the overall unit on this whole thing is inch, 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 which is inch cubed, divided by seconds, which is the unit right there. And it'll be the same units over on this side. Okay, so that's problem 9. Problem 10 is kind of interesting because we have a picture. It says we've got this scuba diver and they're swimming in the ocean, and the ocean changes. This is kind of a weird problem. C is the speed of sound in the ocean. So the speed of sound changes in the medium it is in. So the speed of sound will actually slow way down in denser materials. So like if it goes through diamond, it goes way, way slower than it goes through air or through vacuum. Well, it doesn't travel in vacuum, so nothing going on there. So the speed of sound has a function to it, and it depends on this function by temperature and depth that the scuba diver is diving. Okay, so we're going to do another partial derivative. We want to see, this is another time one, the partial derivative of the speed of sound with respect to time would be the partial derivative of the speed of sound with respect to temperature times dt plus this change in the speed of sound with respect to depth of the ocean times partial depth with respect to time. Okay, dc dt we can find easy enough. Take the partial derivative of this equation. It's going to be 4.6 minus 0.11 t. I think that's right. Let me see what I got here. Yep, 0.11 t plus this 3 will come down and we'll get 0.00087 t squared, and then the 0.016 d goes away. Partial c partial d is real simple. It's literally 0.016. It's a constant. So when I take the partial of speed of sound with respect to d, all of these terms become zeros, and the d goes to 1, and so we get 0.016. Okay, so this is going to be for term 1. This is going to be for term 2. But we need term 3 and term 4. And that numbering I just used is kind of silly, but we can still go with it. Term 3 and term 4 are going to come from these two graphs. Now, first we have to know to find dc dt. We need to know what the temperature is. So we need to know what T is to get a number here. Well, the temperature is based off of this second graph. And they tell us in the problem somewhere, they tell us that it's been 20 minutes. So we go to 20 on the graph and we pull off this number right here. And if you look, it's halfway in between 12 and 13. So the temperature is going to be 12.5 centigrade Celsius. So then we're going to plug this temperature into this equation. And we're going to get a number for dc dt. And I have it written down, so I'll show us in a minute. Now we have to find the change in temperature with respect to time. Well, that's a derivative. But we don't know the function of temperature with respect to time. So we have to estimate it from the graph. So dc dt is the slope of this line right here. And if you look at that slope, that's going to be the change in temperature with respect to time. It's equal to the temperature at time 2, which is 12, minus the temperature at time 1, which if you look closely, it's 13, divided by the change in time, which would be 25 and 15. So it's going to be 25 minus 15. And if you do this, you'll get minus 1 over 10. It's kind of hard to see, I know. You have to zoom in on that graph to see. I just did slope formula. Change in y, change in x. That's all I did. And we're going to do the same over here. So the depth, we're going to look at, I think I looked at these 2 points because they looked like they were pretty close. So this one is going to be the change in depth with respect to time. Well, that's increasing, so at point 2 it's 10 in the y. At point 1 it's 5 in the y, so I'm getting that from here and here. And then the x values are again 25 and 15. So we get 25 minus 15. This one is 5 over 10, so it is 1/2. Okay, now we put it all together. So we're going to say dc dt is this function evaluated when temperature is 12.5. I know there's a lot of work to do there, but what I got for my problem with these numbers is 3.3609 times dt, which we said was -1/10, plus dCdt, which is 0.16, times the change in depth with respect to time, which is 1/2. Let me just confirm that I got all this correct. And if you do this, yeah, it looks good. If you do this, you'll get approximately I'm just looking at this because I use a slightly different slope for depth, and I did get this number right to like 8 decimals. So let's look at that again. So I think I might have used this line. And if we use that line, this becomes it goes up to 15 now, and it still goes down to 5. But now the timeline is different. It's 30 minus 15. And so we end up with 10 over 15, which is 2 over 3. There we go, that's better. So 2 over 3. Now, if you do this, you get, that's not equals. This is that problem stops. Now this problem continues. If you plug all this in, you should get a number like negative 0.3254271. And I don't know why they didn't tell us to round to some number. I wish they would have. But I plugged in all those digits and it just works, so that's great. So how do I interpret this? What this says is that the speed of sound is slowing down. That's the negative, decreasing. So it's slowing down by 0.325 meters per minute. So as this swimmer is going, he or she's experiencing a decrease in temperature as depth is increasing, and so the water is getting denser and colder, which is going to both affect the speed of the sound. Okay, that will conclude Chapter 14, Section 5.